now we have Georgina Cosma. Georgina is a professor of AI in the Department of Computer Science in Loughborough. Loughborough University, where she leads the Neural Information Processing Retrieval and Modeling Research Group. Her focus is, has a lot of focus, but mainly machine learning, machine unlearning, and natural language processing. So now we can.
Thanks, thank you. So yeah, the talk is going to be on machine learning verification. So thank you, Julia, Paris, and Helen for having me. So I'm delighted to be here. So deleting a person's data from a trained model is now something the law requires and something that companies have been already asked to do. So I know the focus of these sessions have been on machine learning, so we're going to turn this round now to machine unlearning, but I'll introduce the basics anyway. So underneath the requirement of deleting data sits a question, that turns out to be challenging to answer, and this is what this talk is going to be about. So before I move on, the work is being done in collaboration with Dr. Axel Finke, who is a senior lecturer in computational statistics at Newcastle University. So I'll present RULA, which stands for Representation Level Verification of Machine Unlearning. So I have to say that this is preliminary work, and we have submitted it to an archive, so you can find the paper on archive, and it's also been submitted to a conference, a dedicated conference in machine learning. So I'll start off by setting the problem, defining some of the measurements that we are proposing in that paper. So I've chosen to just present two today because there's not enough time to cover everything. And then I'll walk through the evidence across the different kinds of data. So, So here's the problem. A company trains a model on people's data. We'll focus on personal data, but it could be on any data. And someone asks for the record to be deleted. So companies run these unlearning algorithms, and these reports that the data's gone. But how can someone check that the data has actually gone? So models can pass the standard unlearning verification checks, the standard unlearning checks, but the data, what you found, is still there. So passing the checks that the field is learning, it's a claim that the data is gone, but not proof. So we've started working on this area. Like I said, it's very preliminary work, but I'll be interested to hear everyone's thoughts anyways after. So what is unlearning? So once a model has been trained, unlearning removes the influence of specific training data from a model without having to retrain the model from scratch. And this is also particularly important for foundation models, very large scale models. So the aim is not to have to train the whole model from scratch if you want to remove a piece of information or a record. So the aim of unlearning is to forget that specific record, but to keep the general knowledge the model has learned from many similar records. So the intention is surgical, so we want to remove the memorized parts and keep the rest. So on this screen you see quite a few applications of unlearning. So privacy, where a person asks for their own data to be deleted, removing biased or incorrect data, content, or associations like biased data maybe for that the model has learned, could be for copyright reasons, and like removing material that the model should never have been trained on, or even like data that's been poisoned from maybe cyber attack. So my focus has been like all the data sets I've used are on people's data, but of course these metrics that I'll present could be applied to other scenarios. It's just we've not tried these yet. So a couple of the headlines. It is a problem, and maybe all of us who are working on machine learning, including myself, should probably start to think, I'm spending all this effort trying to train a model, but what happens if I want to change the model, remove some of the data? So a couple of headlines here. In December 24, European Data Protection Board sets out what's an AI model. That's when an AI model is developed on unlawfully processed data. Regulators may, case by case, and where proportionate, require erasure of the model itself and not just the data set. So in the US, there was a bill that took effect in January 25. It clarified that personal information can exist inside AI systems that are capable of outputting this kind of data, and then Federal Trade Commission required companies, including Ring and I think Analytica I've got on the slide, to delete models as well as the data and the algorithms themselves. So it is an ongoing problem. You know, we will see a lot of people now knowing that the data has been used, you know, to train a model, and there's going to be like requests for deletions. So there we go, and then let's move on. Now I'll start off with the basics, which is terminology that you'll need to actually be able to follow me if you're not familiar with unlearning. So we start with a model that's trained on, I mean, in this particular case, individual people's records, but it could be any records, okay? So these concepts apply to if you're going to use like image data or any other data. So some of these records now need to be deleted. So it might be that is a single person's record, it could be a batch, or it could be, you know, or it could be like a whole class of records, records. So the training data divides into two parts. So the forget set that contains the records that we want to forget, and we've got the retain set that contains all the records that we want to keep. So from there, we create, well, there's three models that matter. So the first model is the original model, which learns from all of the data. The second is the unlearned model, which is that same model, and after the unlearning method has edited that original model. And the third is the oracle model, which is a fresh model trained from scratch on the retained set alone, so it's never seen the forget records. So the oracle is what perfect forgetting looks like, which is basically a full retrain without the record, and which is what we really want to avoid doing, but we do have it because we want to check, you know, the performance of the unlearned model versus the oracle model. So that's the three that's the three models. We've got the first one, which is the forget set and the retain set together, so the original model, and then the unlearned model, which modified that original model, and then we've got the oracle, which is the model that's been retrained without the forget set. Now, a couple of simple but important things to say. So records influence isn't stored in one place, which everyone knows. It's spread across thousands to millions of weights, shown by the red lines here. So you can't just delete a single record. Any update we make to the network affects the entire network. So standard tests in the fields, like MIA, I don't know if anyone heard of it, I'll introduce them in later. So they used to decide whether unlearning worked. So every one of these models that we've tried says, you know, unlearning has happened, that is successful. But then when we looked inside the model with my PhD students and myself, then we look inside the model, we find that to check how it represents things, we found that traces of those records are actually in the model. So we have the same model and then two different outputs. One said successful forgetting, and the other one said, oh, no, actually there's traces of that model, that data in the model. So we've set out three questions. Is there residual at all? Do methods that pass the standard test still leave a trace inside the unlearned model? Then can we measure the trace, and does it generalize? Is the residual consistent across methods and data sets and scales and different types of data? So these are the kinds of questions we set out to do, and we have run a lot of statistical tests, and they're all in the paper, okay, so which has about, I think, about 20 pages of results. So, but I can't present everything here, so I'll just present the main ones. So this is how one of the standard metric works in the field. It's called MIA, if you've heard of it. It stands for Membership Inference Attack. So given a model's predictions, can we tell whether a specific record was in the training data? So it runs on the unlearned model alone and does not need an oracle. Okay, so for each record it takes the model's per sample loss, then a sample threshold on that loss decides which of the groups the record falls in, and the forget records or ones of the models never saw. So the score is how often it gets it right. So when you read that scale from 0 to 100, read it as a distance from 50 and not a score out of 100. So 50 is random, it's a flip coin, it's a coin flip. So anything within that 5 of it counts as a pass, and moving further, and information leaks. So if it's a 65, for example, and a 30, both would fail the test because 30, and also 30 is a bigger gap. So 30 it's 20 points further away from 50, so that would be a worse outcome. So the model passes only when the forget records are indistinguishable from the data it never saw. So that's the first metric, briefly, actually. So, and then I'll move on to these other two metrics, which is the retained accuracy, asks whether the unlearned model still classifies the retained set correctly. And the reference there is the original model, because unlearning should not damage the performance of the data we are keeping. And then we have something called the forget accuracy, which asks whether the unlearned model classifies the forget sets at the oracle's level, and that level is not 0, so we're not looking for 0 values here. And I'll have another slide which explains with an example, because the oracle never saw those records, but still gets some of them right by generalization. And the way any model does on data it hasn't seen, right? So we are not trying to destroy the model, we're trying to keep it working still after unlearning. So the pass condition is forget accuracy through matching the oracle but not falling to 0. So this slide has a couple of examples, well, just an example of how to read this, these metrics. So we just said retain and forget accuracy are each read against the reference, and a group of patients asked, this is just an example, asked to be deleted. The forgotten patient is still diagnosed correctly by generalization. So we never expect accuracy to drop to 0. We write down 2 targets. The retain should match the original model, which is about 86 here, and then the forgets, which should match the oracle, which is about 84. So top row, good at learning, retain 85, forget is 83. Both sit at the targets, so it passes. And the middle row, the model still remembers, forget is 91, above the oracle, so it does better on the forget records than a model that never saw them, so the trace is left. Okay. So similar for the bottom row, forget is 38 and it's below the oracle. So, and this is really important actually, because when you see a difference like that, it means that unlearning has actually damaged the model. So we don't want to damage the model. And so that's how some of the basics there. Now, moving on to some of the unlearning methods. So it's really important to say that new unlearning methods are appearing at a very rapid pace in this field now. Almost all of them are still judged by the same output level metrics we've just seen. So we don't try to cover all of them here. I'm going to mention 5 very briefly. So, and then we're going to focus on the most popular established methods and go through them briefly. But the talk is about verification and not unlearning, as in unlearning methods themselves. So the first group, it's more focused on adjusting weights using gradient steps. So which can actually, a gradient step can improve performance on a data set by reducing its loss, which is what a lot of us do in normal training, or it could, on the other side, be used to deliberately worsen performance by increasing the loss. So increasing the loss on the forget sets is the way, one of these, the way that gradient-based methods work to unlearn it. So increasing the loss on the forget set is what, is a direct way to unlearn it. Now each method chooses which data to use and whether to reduce or increase the loss. Now gradient ascent makes models worse on the forget set, so it's a standard training run, but just in reverse. Then we have netgrad class, which is very popular, does both at once, making the model worse on the forget set while improving performance on the retained set. In the same update, fine-tuning continues learning on the retained sets only and never shows the model the forget records again. Just basically what this does, it relies on catastrophic forgetting to remove information about the forget set. And now very briefly, we've got the group on distillation, which is student-based models. So we train a student model to imitate a teacher, and the methods are different in who that teacher is. Scrub uses the original model as a teacher and asks the student to match it on the retained set and diverge it on the forget set. And then bad teacher, so we modified it slightly so we could, for comparison reasons, and so we could compare it to Scrub. So bad teacher in our version uses an untrained model as the teacher and ask the student to imitate it on the forget records. And the reasoning is that a model which never saw those records provides the closest available reference to never having trained on them in the first place, while the true labels keep the retained set accurate. So that's that, and you don't need to remember the details of these methods actually for the rest of the talk. It's just I wanted to show that there are two different types of, two groups of methods when it comes to unlearning. But like I said, there's new ones coming out pretty much very rapidly. Okay, so a set of metrics takes any unlearned model, and no matter how that was produced, and checks it for residuals. So we check the model, we check we check whether there is any residuals left after unlearning at record level. Now, it is important to say, like, to mention the three different types of checks. So we have the parameter level compares the weights directly. Do I have only 20 minutes left, or no?
25.
Okay, I'll just try to speed up a bit then. So the parameter level compares weights directly, but the same function can be encoded by very different weights. So two models can behave identically, can sit far apart in the weight space. So weight distance can't tell us whether a record was removed, and there is research done on this which shows that parameter level comparisons can't certify unlearning. And we've got the output level metrics, which we've seen, the MIA, retain, accuracy, and forget. So the limit with them is that a model can pass those metrics and still hold the forgotten records. So we focus on the representation level, which is the third level, which is on this list, and when we compare the internal embeddings record by record. Okay, so I present two of the four metrics. Now, so there are two ways the model encodes information about a record. So the first is a unique trace of that specific record. So the model saw the particular row and shaped some weight around it, and that trace is what unlearning is supposed to remove. So the second is a shared pattern, something learned across many records that happens to apply to this one too. So unlearning must leave that intact, because removing shared patterns from a record damages general performance. Okay, so, and then as I mentioned, I think before, classifying the forget record that correctly is not a problem, it's what we want, and the oracle that never saw the record classifies it correctly too by generalization. So the difficulty is the verification stage. So we can have a correct prediction, and this is really important actually. You can have a correct prediction which can come from either source. It can come from a residual trace, okay, that's left from the record, or it can come from a shared pattern. And an output test, like MIA and the other two we've seen, are not able to, are working at the output level, okay? So, which just see the prediction and not where it came from. So a MIA test can tell you that something has been unlearned, but it's just looking at the prediction and they didn't see where it came from. So what I'm trying to say is that it could have come from the shared pattern or the actual residual that was left in the record. So we never know that unless we actually look at the residual. This is just a slide on the experimental set, but I thought I'll introduce this first before we start looking at some of the results. So, and it's actually really important because my PhD student, Jamie, found that there is a lot of variation in the way experiments are done in the field. So he actually submitted a paper as well on kind of good approaches to evaluating machine learning. So we start with, first is the training. So for each data set, we train a model on all of its records, gives us the original model and one that has seen all the data. So we repeat this 10 times, each with a different seed. So each run starts from a different initial weight. That gives 10 original methods or models per data set, and every later result comes from all those 10 runs. So we have the forget request after that. So before any unlearning, we pick up random, a fraction of the training records to be the forget set. So we try three sizes, 1%, 5%, and 10% of the training data, and everything else stayed in the retained set. So for each fraction, we also train an oracle from scratch on the retained set alone, and remember the oracle is the model that has never seen the forget set. So when we unlearn, the unlearning step is deterministic, it uses one fixed seed, so the only thing that changes between the runs is which trained model we started from. Okay. So what you see on this slide is, I haven't introduced them to you yet, but I will do soon. Just I'm going to show you some of the preliminary, one of the results to explain, and then we'll go more into detail in the next slides. So both panels here just show their results for the 5% forgets, and that's about 100 models each. So panel A is the output of MIA, which is the membership impairment attack, so one of the standard methods used in the field for evaluating machine learning performance. So at thresholds, and then it cannot separate the forget records from records the model never saw. So at the output level, unlearning passes. So you see kind of all the centers around the 0.5, which, and then there is, when we're looking at the results, show that, okay, learning has been successful according to MIA, because it did look at the output level of the models and not the internal representation. But then using one of the metrics we've developed, which is a very simple one actually, we can see a gap, and then 0 means that the forget records sit as close to the oracle as the retained records do. So below 0, and then they sit further. So all 4 are below 0. And MIA and M2 run on different scales. That's why I've got kind of different axes there. And so we see that if we look at the M2, unlearning has failed, but if we look at the MIA accuracy, unlearning has passed. Now, that was just like a little bit of a taster, but I'm going to come back into those results soon. So when we say ruler, what do you mean? It's a set of metrics that work at the representation level. So so we have chosen the last layer, and I will explain why. So that's the penultimate layer, which is the activation immediately before the final prediction head. So for a given record, that layer produces a vector. Okay, so it's called the embedding, which you're familiar with, and that vector is where the model places the record in its internal space. So in the tabular setting, the vector has about 128 dimensions, and we normalize it to unit length before doing anything with it because we care about the direction. So you might be wondering why this layer. So because earlier layers tend to encode more generic features, so record-specific information is often less pronounced there, and this final layer collapses everything down to class scores, which throws the record level geometry away. So that's why this layer sits between the two, making it a natural place to explore record-specific representations. So this matters for the further experiments I'm going to show. So it's the same kind of architecture selection. So for every model, we take the activation immediately before the prediction heads, and I'll show you some examples. So this is the first metric, which doesn't need an oracle. So it needs an oracle. So for each forget record, we take the cosine similarity between the embedding of the unlearned model, okay, which we never saw, and then, so that is basically to measure how closely the unlearned model places the record where the oracle should. So this comparison works if the two models are aligned to start with, so the original and the oracle trained from the same seed. And when we tried this, they do agree on 0.99 cosine, but and that's against the 0.43 for different seeds. So we train each oracle from its original seed, and then the unlearned model keeps that alignment. So what M2 is basically a calibrated gap. So it's the forget mean minus the retained median of these alignments. So subtracting that baseline is the calibration, and it fixes 0, so the gap reads the same across data sets. So probably wondering what 0 means then. 0 means the forget records match the baseline and erasure has worked. So below 0, there's a residual or a trace, and above 0, the forget records sit closer to the oracle than the retained records. So we use the median on the large retained set, so a few outliers can't inflate the baseline, and the mean on the small data forget set, so a single residual record still counts. So what this chart shows basically is the results of the first experiment, which tried to answer the question, does each method remove the trace or leave a residual? So we measured each unlearned model against the oracle. So M2 measures whether the forget records sit close to the oracle as the retained records. So in the left panel, checks the baseline, so we compute M2 between pairs of oracles. Each retrained with a different seed using the same formula we use for the unlearned model. So neither saw the forget set, by the way, so M2 should be 0, and across the pairs it centers on 0, and this makes 0 calibrated baseline. And on the right panel is the test at 5% forget, so each box is one method. Here, over 100 runs from 10 data sets and 10 seeds, and every method's box sits below 0. So the forget record sits further from the oracle than the retain record, and then this is residual, and that's basically a residual trace. So all 12 conditions, 4 methods, and all 3 forget fractions, so the 1, 5, and 10 are all negative. So 10 are significant under the mixed effects model. So, so 10 of the conditions are significant under the mixed effects models, and the other 2, gradient ascent at 1 and 5%, are still negative and not just significant. So this direction holds everywhere. And you might be wondering, actually, the residuals are small, but we did test that to find if there is any significance there, and there was. So the previous slide shows M2 gaps are very small. The question here is whether a gap that small is signal or is it noise. But there are a lot of details in this in the paper, and I know that you find the statistical results there. But the main message is that every method's distribution is centered below 0, and under the mixed effects model, the gap is negative and significant in 10 of the 20 conditions. So I'm going to move on to M4 now, which is the second metrics that does not need an oracle. So it asks a different question, and this time it is we ask whether a forget record is embedded like a retain record. So everything comes from the unlearned model's own penultimate embeddings, and for each record we find its nearest neighbor in the retain set by cosine similarity, and we do the same for each retain record against all the other records. So the second step is our reference on how close a retained record sits to its neighbors. So what matters is which direction counts as a residual. So this is again a very important point, because a removed record should look like any other retained record. And if a forget record sits closer to its neighbors than the retained record does, then the model is still treating it as one of its own training records, and that extra similarity is a residual. But if it sits no closer, it looks like any retained record, erasure has worked. So it's just a typical record that's been projected and sits in a typical way in terms of closest to the other retained records. So what I'm trying to say is that if it sits no closer, and it looks like any retained record, erasure has worked, but if it's pushed much further out than the retained records, then we have over-erased. So you might be asking, why 0.5 as a set? It's by construction, M4 is a percentile rank. So a record that's indistinguishable from the retained set will fall at a random position in that distribution, and that averages the median to 0.5. Okay, so empirically the settings were nothing showed that nothing was memorized actually. So I will move to the next slide and explain more. So this is just an example of how the M4 works. So we have a number which each record gets, and then for any records we take its cosine to the nearest neighbor, to its nearest neighbor in the retained set. Higher cosine means that it sits nearer. And I'll just skip to that. So what we see here is 9 out of the 10 sit below it and below the 0.96, and then only 1 is at 0.97 nearer, so the fraction is over 9 over 10. So if you read this as a percentile, at 0.5 the forget record would sit in the middle, no nearer than a typical retained record which has been erased, and at 0.9 it's nearer than 9 of the 10, closer to the retained set than what is a normal record that is found in this data set. So I've used a small example here, but just to illustrate the point. So this is mainly the kind of the idea. So membership inference attacks ask whether a model forgot enough, it can't see over erasure, but when unlearning is too aggressive, it does not just remove the record, it distorts how the model represents what a record represents that record, and that damages the model. So M4 reads the representation, and it's two-sided because it sees both. So the M4, so if you're in the middle is 0.5, so oracle level, what successful unlearning should look like. Above 50 is residual remains, so the record is still too close to the retained records, and below is over erasure. So we'll see soon one of the very popular methods called scrap at 1% for get sets, which reaches M4 at 0.24, which is well below the null. So scrap didn't, so one of the methods like scrap didn't just remove the records, which was an identity data set, it distorted the representation around that, but the residuals of that record and the data of that record was still in there. I'm going to skip this one. So, and so far we've read like M4 after unlearning, but what we found that M4 has two uses. So we can also use it to find out whether the model has memorized. So reading's very, so we gave it like a lot of data sets and large scale ones as well. So we've run M4 on the original model on its own, and it answers a different question if there is anything memorized. So the readings vary a lot across the settings. Most tabular data sets sit at the null around 0.5, with two showing memorization around 0.55 to 60, so it's moderate memorization. Image data and the clinical text data sit at the null, so nothing was memorized. But then the face identity data set reached 0.94, which was a strong signal of memorization, with the forget person's images bound far tighter than the retained set. So before anything and any unlearning method is applied, the question is, do we really need to remove that to apply unlearning to those records if the model has not actually memorized the records in the first place? So this is what we see, because if we do apply an unlearning algorithm to a model that never memorized the record, we're going to destroy the model. And this is what we're trying to avoid. This slide just shows the M2 and the M4 metrics, and it's not always easy to get an oracle. So we're trying to avoid having to have an oracle in the first place, which means retraining everything from scratch without the forget sets. So our M4 is oracle free. But obviously, for research purposes and to evaluate models, we do need to have an oracle. So I'm just going to move on to some of the evidence we've done. So I've mentioned bad teacher at the beginning. So when we did apply bad teacher, as well as we just held back this method, and then because it has a different mechanism to the other ones, and it's distillation from a randomly initialized method. So if the residual were peculiar to the specific gradient method, then this would disappear, would see different results. But actually, it's all very consistent. Residuals didn't disappear. Bad teacher also left residuals, which were clear at the 1% and fading to the null as more records basically were removed, or the forget set got larger. Okay, so we are consistent there. Now, the M4, with the M4, before the per dataset breakdown, before I show you that in the next screen, here is what we read M4. So it's really important to read it as a one data set at a time. So we measured how much of M4's variation comes from the data set itself. So 89% of the variation is between data sets, and only a small part is anything else, including the method. So what this means is that whether memorization shows up depends on the actual data sets. So pulling everything into one number to show like the results across 5 data sets into like a box plot is not going to be helpful. So we won't pull, so pulling everyone into one number, it would just mix the data sets that memorize with the ones that don't. So it's really important to apply this to a specific data, which is what we've done. So we took all the 10 data sets, initially the tabular data sets, and we only found that only 2 showed memorization. 1 was borderline, and the rest sat at the null. So then, which explains why unlearning methods, kind of tend to destroy the models when they apply to this. So we did try large-scale tabular data sets as well, so 2 of them over 100,000 records. So these are very popular data sets. So it's the covered type and Higgs, which are very large tabular data sets. And we found that again, okay, so so each cell is the same for read from the penultimate embedding, no oracle and no retraining, again the 0.5 null. So the original row sits at the null throughout, so nothing was memorized at this scale. And the red cells are with the network class rising to 60 on the Higgs transformer, which basically shows, so if you look at the original, that can compare the rest of the results, there was pretty much not much memorized. So those aren't a residual, they're just learning on steps from the distortion. So we basically here applying the learning methods like the literature does pretty much not really have much effect. So here is, I wanted to show this image because it just shows how we extract the penultimate layer using another network. So this one is on image. So you're familiar with CFAR 10 and 100 and the SVHN dataset, which is true view house number digits. So it's a much more complex dataset than the most common digit dataset that's CPN is using. I don't name now. Okay, so as before, we take the activation layer before the classifier normalize it and compute M4. Okay. So again, on this data set, the original shows rows sit at the null again. Nothing was memorized. So the CNN, the methods stay at the near the null. On ResNet 18, the red values, netgrad plus and scrub fall well below the null. So that's over erasure. Since the model had memorized nothing, we've seen distortion. Okay. So also on biobirds, clinical biobirds, so this is kind of how we extracted the layer from there. And so M4 reads 0.54 1%, 52 at 50 and 5%, and then, so M54 is borderline. Again, no specific record was really memorized, okay? Now, I'm gonna move to something a bit more exciting here, which is an experiment we carried out using a face data set. So the aim is to test whether a model memorizes identity when its training never asks for it. So we trained the model not on identity, okay? So we didn't say, here is a picture of a person A, predict person A. No, we didn't do that. So I'll explain what we did in a second. So the model is a ResNet trained on labeled faces in the wild, which has 4,324 faces across 158 identities. So we trained it on gender, which is not a task that I'll advise you to do. It's just like for experimental purposes. So the label is gender, which is a coarse binary task. So identity is never part of the classification objective. The forget sets is every image of one person, since a real deletion request targets an individual, okay? Not a set of random records. So gender is a deliberate choice here. If the model had been trained to recognize identity, because the train put it there, so then we'd expect it to classify. So if the model had been trained to recognize identity, finding identity afterwards would prove nothing because the training put it there. But with gender, identity is never part of the objective. So if it still shows up in the representation, the model memorized someone, but when it was never asked to do so. So this is a controlled test of what the representation retains and not a system that was built for real world use. So I wouldn't advise you to train a model to identify gender specifically. So M4 is computed on the original trained model, again as before any unlearning. So for each image of the forget person, M4 takes the cosine similarity to its nearest neighbor in the retained set, as I've explained before, and on the penultimate 512 dimension representation after global average pooling, then ranks that against the retained records or values. So remember that a score of 50 would mean no memorization. The person sits no closer than chance. So we got a result of 0.94, which in percentile terms is this person's images sit closer to the retained set than about 94% of retained records do. So the model was never asked to do this, and identity is already encoded in the representation before any unlearning is applied. So the table runs in after unlearning. On each unlearned model, are 3 forget fractions average over 5 seeds. So the original sits at 0.94, 1%, and stays well above the null. So we have 3 methods here: gradient ascent, negrad, fine tuning, leave them for between 0.65 and 91. So identity is still encoded, and the deletion didn't reach the model. So scrap is the exception here. At 1%, it drops to 0.24, which is well below the 0.50, which means that the forget records have been pushed further from the retained set than the retained records are from each other. And that's basically model distortion of the representation, and it's not erasure, so it's not deletion. So either way, the conclusion is the same. You know, none of the records returns M4 to the null. Okay. So nearly done. I have another 5 minutes, or is it? Yeah. You have more time? No, I'm gone. I'm done with that. Okay. Okay. So, so what does M4 really do? It detects the presence of memorization. So on the face identity, it reads 0.94. The targets, so the forget record sits at the top of the retained similarity distribution. So the model has memorized individual identities. So it detects the absence of memorization. On image and clinical text, it sits near 50, and the forget records match the retained set, so there's nothing unlearning to remove. So I won't repeat again, you know, what I've said before. So across every setting, you know, the pattern is the same. Memorization is the exception. The strongest where individuals are distinctive, faces are there, or it's a small medical data set. It's where, you know, models memorize something, a record. But then, you know, we've seen in the field, you know, there's a lot of unlearning on data sets like CIFAR and CIFAR 100 and all these data sets where, you know, the models are not trained to memorize a specific, you know, individual, as we've seen in these kind of cases. Now, something really, again, another important point here. So we've got M2 and M4. M2 is offline. Before deployment, we retrain an oracle and use M2 to test that the unlearning method works. It's a statistical population test. Online per request we use, so if we're going to use something dynamically, like we're going to have online per request, so we use M4 to verify each deletion. So it's cheap, and you don't need an oracle, you don't need to retrain a model from scratch without the forget sets. Here is an example. Patient asks for the records to be deleted. So first we do a pre-check. Okay, we compute M4 on the original model. If it's around 50, the records were not memorized, so we skip unlearning. There is no need to apply it, because running it on a model that did not memorize, it's just going to distort the model. But if it's above 50, we apply unlearning, and then we verify, we compute M4 again on the unlearned model, and then if it's back to the null, the deletion worked, and we deploy it. If not, unlearning was incomplete, and we escalate. So at fear of 0.5, after unlearning means a success, only because the pre-check found memorization to remove. So alone 0.5 could mean nothing was there. We have done a lot. I'm not going to go through the entire table, it's just only a small part of it, of what I've explained. But to go back to the questions, there are residuals, we can measure them. It does generalize across data sets, and this is just a very preliminary work I've described here. It's just the starting point, but we do have plans now to move away kind of from unlearning, developing unlearning methods themselves, to verifying whether we need unlearning methods in the first place, to focus on the metrics of verifying that deletion has happened. It's really important because of like multimodal unlearning as well, brings a bigger complexity, you know, cross-model learning where we use, we train methods using different types of modalities of data. You know, how do we unlearn when, you know, when data from one modality transfers to another? So things get more complex, and then with continual unlearning, is also an interesting one. You know, how do we check model drift? How do we track changes in these residuals as more data is added during the continual learning process. Another very interesting aspect is the legal and the regulatory, so working with legal experts to connect representation level evidence to GDPR Article 17. So we do measure whether there is a residual there. You know, people would say we delete my records. So is deletion, approximate unlearning enough to satisfy the legal requirements of say GDPR? So we don't know that yet. And thank you for listening. Oh, by the way, I mentioned Jamie and I mentioned Petros, so they are also working, they're my PhD students, they're working on unlearning. Petros developed a framework for experimenting with unlearning, and actually Jamie also contributed to that because he developed best ways to evaluate and the methodologies to evaluate unlearning by looking at the different papers in the fields. So best practices, and then the Supreme, which is a framework for unlearning. So these best practices are embedded in Supreme. And then me and Axel started working on verification, and then now Jamie is also looking at verification because he's also finding that starting with unlearning and looking at the results of unlearning at the output level, they don't tell the full story and residuals still remain. So I'd love your thoughts on this, any ideas for improving things, or collaborations especially welcome. Yeah, so thanks for listening.
So thanks for the presentation. We have time for one or two questions.
Thank you for the interesting talk. So this might be a silly question. I was wondering that what's the difference between unlearning to if you construct a data set that you kind of hidden the identity or mess up with the identity, then you train the model on this kind of data set. The kind of learning to give output that doesn't give relevant information for that.
So what was the question?
So it's like instead of doing unlearning, you construct a data set that's, for example, for the identity example, you hide the identity or mess up with the identity. Then you train the model on that.
So you're thinking of introducing noise within that particular identity to destroy the. Yeah, so that's another kind of, maybe it's a type of machine learning. So, but then again, we'd have to measure how much residual there is after the model is destroyed. So this is where the metrics come in. So that would be the an unlearning procedure to say impute noise and destroy it. But then, how would you evaluate that? Yeah. So this is again, it's around also about catastrophic forgetting. I was probably expecting a question on that, but then again, it's different. You know, to measure a catastrophic forgetting, you need like the metrics, that's the verification metrics that will come after this. Yeah.
One last question, I think.
You've done a lot of like extensive evaluations across a lot of different modalities. I'd just like to, this is just out of curiosity, so like in the example with the high residual report that when you train ResNet 18 on LWF, you said that you retrieve those results across like averaging across 5 different like training runs or something like that?
Yes, pre-training seeds, because 10 took a long time, I didn't have the, the results,
did you also look into like what would happen if you, let's say, use different varying degrees of data augmentation, different training objectives, because this was binary classification, right? And like if you tried those and if you haven't tried those, would you think that it might result in a slightly different residual, or would you think it's still going to be high?
So as in, say that, so what was the question then?
So the question is like if you tried like different training settings, like more different objectives, different data augmentation, would the remembering or like the high residual still hold, you think?
So we trained on gender specifically, which we're not meant to, but then we found I identified faces because it sat the record closer to the retained set of those specific faces. So you're thinking of like if I kind of, so what was the question? I'm trying to understand.
So like let's say if you
trained on other objects, not gender, you mean, trained on something else. So it would still probably identify faces because faces was never part of the objectives. So that would change the classification task, but because because this data set contains groups of images of faces, it would still probably, my guess is it would still probably keep them in. But yeah, it's interesting that you've said that actually, because gender, it may have linked some features of gender to certain faces. So something actually, I might try that. Yeah.
Thank you.
So now we have lunch,
Okay.
but I think
Thank you.
everyone can speak with you during lunch.
Everyone, yeah, I'm very interested to hear everyone's thoughts. If you spotted anything that could be done, further, yeah, happy to discuss. Yeah.
Thanks.